Hello, thank you for joining us for today's webinar on thin film RTD temperature sensors. Today, we'll learn all about RTDs, how they work, how they're fabricated, and how they're customized. Today's webinar will consist of a few different topics. First, we'll review the different types of temperature sensors available in today's market. Then we'll discuss how thin film RTDs work and what the benefits are. Then we'll narrow our focus on thin film RTDs, where we'll discuss TCRS, characteristic curves, response times, and phenomena like sensor self-heating. Next, we'll go in depth and review the IEC 60751 tolerance standards and the tolerance curves for the different classes. We'll end with a trip to the clean room, learning how the RTDs are made, and then we'll explore the many ways that the sensors can be customized for individual applications. Temperature. Why do we measure it? In many sectors, temperature is one of the most important physical parameters for determining product quality, security, and reliability. The applications for temperature measurement are endless, but there are several common ones that come to mind, including process control and automation, HVAC, handheld devices, medical, biotechnology, aviation and space, appliances, and automotive. The list goes on. Since there are a wide variety of applications where temperature measurement is necessary, many types of measurement technologies exist. Some are more suitable than others for certain applications. Today, we'll focus primarily on thin film platinum RTDs, but let's quickly review some other technologies. Since there are a wide variety of applications where temperature measurement is necessary, many types of measurement technologies exist. Some are more suitable than others for certain applications. Today, we'll focus primarily on thin film platinum RTDs, but let's quickly review some other technologies. First up, we have the NTC Thermistor. These are made of semiconductor material. They're nonlinear resistors which alter their resistance characteristics with temperature. These have a negative temperature coefficient, meaning the resistance decreases as the temperature increases. The resistance is measured by measuring the voltage drop. Next, we have the thermocouple. This consists of two dissimilar electrical conductors, which produce a temperature-dependent voltage as a result of the thermoelectric effect. This voltage can be interpreted to measure temperature. Unlike most other measurement methods, thermocouples are self-powered and require no external excitation. The main limitation, though, is the accuracy. It's difficult to achieve less than a 1 degree C system error. Next, we have semiconductor temperature sensors. They are usually created using silicon that has been doped. A small amount of impurity is mixed into the silicon crystal, shifting it from a good insulator to a viable but not great conductor, hence the name semiconductor. This conductivity changes with changing temperature. Some semiconductor temperature sensors, like the TSIC family from IST, have built-in integrated circuits, enabling them to be pre-calibrated and to deliver either an analog or a digital output. Lastly, we have the resistance temperature detector, or RTD for short. These are also sometimes referred to as resistance thermometers. Before we discuss these, it's important to have a general understanding of resistance. Resistance is a measure of how difficult it is for an electrical current to pass through a conductor. When current flows through a conductor, like a metal wire, the moving electrons can collide with the atoms in the metal. Unlike NTC thermistors, the conductive elements of RTDs have a positive temperature coefficient. When the temperature increases, the electrons exhibit more collisions and the resistance increases. The opposite is also true. According to Ohm's law, the resistance of a conductor is equal to the voltage across the conductor divided by the current flowing through the conductor. This simple relationship is what we generally use when designing circuits for resistance measurement. Now let's explore some common RTD types. First up, we have the wire-wound RTD. Wire-wound resistors were one of the first forms of commercially available RTDs, and they have changed quite little over the years. A wire is wrapped several times around a ceramic cylinder, then it's covered in glass. Or the wires are coiled and potted in ceramic powder. These images show the two different constructions. The resistance of the sensor depends on the number of coils, or the length of the wire diameter, and the wire resistivity. Wire wounds are usually named based on their resistance value, like PT100, meaning the resistance is 100 ohms at 0 degrees C. We'll learn more about nominal resistances a bit later. Finally, we have thin film RTDs, which we'll discuss for the remainder of the webinar. These generally consist of a ceramic substrate with a very thin conductive metal film. The most common metals used are platinum and nickel. Just like the wire-wound RTD, the resistance depends on the length, diameter, and resistivity of the conducting element. But instead of wrapping wires around a cylinder, thin film RTDs feature what we call a meander structure, pictured at the top left. This layer is generally only about 0.1 to 10 microns thick. There are a number of different construction examples ranging from wired to cylindrical to surface mounted. Thin film RTDs also have a nominal resistance. For platinum, the most common are PT100 and PT1000. With so many temperature sensing technologies available, what makes thin film stand out? The thin film RTD is one of the most accurate sensor types and covers a broad temperature range. They are very stable, demonstrate good noise immunity, have excellent repeatability and linearity, and are very vibration resistant. Let's see how the thin film RTDs compare to some other sensor types. When compared to wire-wound RTDs, thin films are less fragile and more vibration resistant. Thermocouples are a rather inexpensive option. Like thin films, they are rugged and operate over a wide temperature range, but they deviate significantly at extremely hot or cold temperatures. Thermistors operate with very low reference currents and lower energy consumption, but offer accuracy in a more limited range, typically -90 C to 130 C. Lastly, while semiconductor-based sensors have a small footprint and are easily integrated with ICs, they are slow to respond to fast temperature changes. They also only operate over a limited temperature range. In short, all sensor types have their pros and cons, but thin film RTDs are a great all-rounder with great temperature range, stability, and repeatability. Nickel and platinum are the most commonly used metals for thin film RTDs. Historically, nickel was cheaper to produce than platinum. It's also almost twice as sensitive. Nickel sensors offer a great range of customization, with TCRs ranging from 4280 to 6720 ppm per Kelvin. This makes them a great option for replacing discontinued sensors. Now on to platinum. Nowadays, the process and manufacturing costs for nickel sensors are higher than those of platinum. Since platinum sensors already boast better long-term stability and a broader operating range, platinum sensors are generally preferred. Plus, modern electronics make up for the difference in sensitivity between the two sensor types. One important thing to think about when selecting sensor materials is thermal compatibility. Materials should be thermally compatible, having similar coefficients of thermal expansion, or CTEs. The CTE determines how much a given material will expand with a certain temperature increase. For a thin film RTD, the ceramic substrate, the platinum thin film layer, and the glass protective layer should have similar CTEs to avoid cracks or inaccurate resistance readings caused by mechanical stress or strain effects. An easy physical way to illustrate this is if you imagine a balloon with a piece of tape on it. If we let the air out of the balloon, the tape will remain the same size, while the balloon will shrivel and become smaller. With RTDs, if there's any deformation, we want each layer to deform by the same amount, unlike the balloon. Typically, when we see a platinum RTD, it's called something like a PT100 or PT1000. This represents the resistance of the sensor at 0C. Different applications and customers call for different nominal resistances. Let's take a look at the two types we mentioned. Both follow the same overall temperature polynomial, which we'll discuss on the following slide, but the PT1000 resistance values are larger by a factor of 10. This is important when we consider things like wire resistance. If we use platinum wires, for example, whose resistance varies greatly with temperature, our total resistance will be higher and our final temperature reading will be higher than it should be. These effects are less noticeable with a PT1000 since the RTD's meander resistance will further outweigh the resistance of the wires. So in applications where a two-wire sensor is needed and we have no way to compensate for the wire resistance by adding another wire, a PT1000 is a safer bet. PT100s are a more common sensor, and it's generally a better option when selecting a sensor to replace a wire-wound RTD. That's because historically, it was pretty impractical to make a wire-wound RTD of 1000 ohms, as it would be quite bulky and fragile. Another consideration is the applied current. To avoid significant self-heating effects, we limit the applied current for different types. We'll go more in depth about self-heating a little later. One of the key parameters when selecting an RTD is the TCR, short for the temperature coefficient of resistance. This value is a calculation of the relative change of resistance per degree of temperature change. It's typically expressed in parts per million per Kelvin. A commonly used TCR for platinum is 3850 ppm per K. Some applications require different TCRs. We'll get into this a little later when we discuss customization. For now, let's take a look at some values for other variations of platinum. Where does this number come from? We simply take the resistance at 100C minus the nominal resistance divided by 100 times the nominal resistance. While the TCR gives us a broad look at how the platinum behaves, in order to accurately calculate our temperature, we use a temperature characteristic curve. The curve follows this polynomial equation, the coefficients of which are different for each platinum variation. Here we see a sample curve for a PT100 sensor with 3850 ppm per Kelvin platinum. As you can see, it's quite linear for the sensor's operating range. Thin film RTDs are made available with different tolerance ratings. The tolerance refers to the allowed measurement error at a given temperature. Different applications call for different tolerances. For example, a medical device might require a tighter tolerance than an HVAC application. Tolerance values are usually given in degrees Celsius or as a percentage of the temperature reading. For example, let's say the tolerance is plus or minus 3 degrees Celsius. For a temperature of 100 degrees C, anything from 97 degrees to 103 degrees C is acceptable. Now let's say the tolerance is plus or minus 2%. For a temperature of 100 degrees C, anything between 98 degrees and 102 degrees C is okay. Here's an example tolerance curve for two classes of nickel sensors. It's important to note that the deviation is an absolute value, meaning it can be an error in the positive or negative direction. Also, note that the tolerance is different here on the positive and negative temperature range for nickel. For platinum, it's symmetrical around 0 degrees, or the y-axis. RTDs are typically classified based on how they conform to the IEC 60751 RTD tolerance standards. We can see the different classes below. Each class corresponds to a different deviation formula, which is valid for a specific temperature range. IEC and DIN standards and classes are the most common ones you'll encounter when working with RTDs. Let's take a look at an example. What is the allowable deviation for a Class B sensor at 400 degrees Celsius? We can plug in 400 to our Class B formula to get an answer of plus or minus 2.3 degrees Celsius. We spoke a little before about tolerance curves. Here are what the curves look like for the IEC 60751 tolerances for platinum RTDs. Again, it's important to remember that these deviations can be in the positive or the negative direction. In order to assign a tolerance class to a sensor, we need to test the sensor with at least 2 temperatures. At IST, for our wired sensors, we dip each sensor into well-controlled baths, each at a different temperature. Based on the temperature measurement of each sensor, our algorithm assigns it an IEC 60751 class. For this classification process, it's important for us to specify the measurement point along the sensor's wire, in case the wire is contributing to the resistance. The influence is lower for silver lead wires, but it's greater for nickel gold wire, nickel platinum wire, and especially for pure platinum lead wires. For most sensors, we measure at 5 millimeters from the wire's end. For long wires, over 20 millimeters, wire resistance is compensated at room temperature to ensure the resistance at the chip's edge. Another thing to keep in mind when selecting a sensor is a phenomenon called self-heating. What is self-heating? Let's imagine an electric stove. Once it's turned on, current runs through the coils and heat is released. The same thing happens with the sensor's meander structure. It can influence the sensor's ambient temperature measurement. It can be compensated for with electronics, or it can be minimized by choosing the appropriate sensor and carefully controlling the maximum current. In general, the applied current should be as low as possible in order to reduce the self-heating effects. Some maximum operation current suggestions are listed below for different nominal resistances. The self-heating effects can greatly depend on the sensor's application, though. For example, when applied to a metal surface or inside a probe with heat-conducting paste, heat release time may be faster and will have a more accurate ambient temperature measurement. Lastly, self-heating is highly dependent on chip size. For small chips, the self-heating effects can become significant. Some of IST's standard chip sizes are shown to the right. For smaller chips, we have a smaller mass, and the heat release is concentrated on a smaller surface. On a larger surface with higher mass, the heat can be released more easily and more quickly. Let's consider this illustration. If the same amount of water is poured into 2 bowls of different widths, from which will the water evaporate fastest? It should be the bowl on the right, where more of the water's surface area is exposed. In general, a larger chip size will exhibit less self-heating. IST uses this formula to calculate the self-heating effects. The change in temperature is equal to the resistance times the current squared divided by a self-heating coefficient. The self-heating coefficients for common chip sizes are listed in the Platinum RTD application note on our website. Response times are also dependent on chip size. Here we can see the response time in seconds for several IST chip sizes: T0.5, T0.63, and T0.9 are the times it takes for the sensor to reflect 50, 63, and 90% of the temperature change, respectively. For example, when heated from 25 degrees C to 75 degrees C, a 202 or 2 mm by 2 mm chip will take 0.11 seconds for the sensor to reach 50 degrees C, which is 50% of the temperature change. Many customizations improve response time, including metallizing the sensor backside, potting it in a thermally conductive housing, using thermally conductive paste, etc. Before we get started on the customizations available for RTDs, let's talk about how we fabricate them. The first half of the sensor fabrication takes place in a clean room, where temperature, humidity, cleanliness, and air quality are all carefully controlled. If you've worked in semiconductor fabrication or MEMS fabrication before, you're probably familiar with some of these processes. Thin film RTDs are typically constructed on a thin ceramic substrate. There are several substrate thicknesses to choose from, including 0.65 mm and 0.25 mm. A typical substrate can hold hundreds or even thousands of sensors. First, we start out with our bare substrate. Then, we load it into our sputtering machine, where we'll deposit platinum using a process called Plasma Enhanced Physical Vapor Deposition, or PEPVD for short. A block of platinum called the target is loaded into the machine. Then we shoot an ion beam at the target. Platinum will separate from the target and splash back at the substrate. After some time, we're left with a thin, uniform platinum layer. Several substrates can be coated at once using the same machine at the same time. The resistive layer is then coated with a light-sensitive photoresist. The room must be wrapped with a yellow light film in order to protect the photoresist. If you've ever worked in a photography darkroom, the setup is similar. The photoresist is applied to the substrate using a process called spin coating. First, the photoresist is applied in the center of the substrate. Then, with high-speed rotation, the resist is applied evenly on the entire substrate. The coating is subsequently dried on a hot plate. Now that our photoresist is applied, we can perform a process called photolithography. We take a piece of glass with a metal drawing of our platinum meander and contact pads. This is called the photomask. Then, we align it closely with the substrate and a brief burst of light is applied. Only the parts left exposed by the mask are exposed to the light. These exposed areas are washed away during a subsequent chemical development process. Now it's time to get rid of the platinum that's not part of our meander and contact pads. For this, we use a process called ion etching. After etching, only the platinum that's protected by the photoresist remains. When we remove this resist, we're left just with our platinum meander and contact pads. Next, we use a process called laser trimming to check and adjust each sensor's nominal resistance. Each sensor contains a ladder-like structure which we can use to adjust the resistance. The sensor's contacts are probed and the resistance is checked. If the resistance is too low, we zap a rung of the ladder with our laser, lengthening the path of the current and increasing the resistance. Once the resistance is in an appropriate range, we move on to the next sensor. Sometimes a lithography defect can cause a short or an open circuit in the meander. In these cases, the resistance will be very far outside of the acceptable range. The sensor can then be marked for rejection by scoring through the whole sensor with the laser or by marking it with ink. Then it can be sorted out during future electrical and optical inspections. While the nominal resistance is technically measured at 0 degrees C, the trimming process occurs at room temperature. Since the laser itself heats up the substrate temperature is considered during the trimming process. Two screen printing steps are then performed on each substrate to strengthen and protect it. The first screen printing step reinforces the contact pads so it's easier to weld. We first start with our bare substrate. Then we apply a screen printing mask. A conductive platinum-based paste is pressed onto the substrate through the mask. When the mask is removed, we're left with enhanced contact pads. Our second screen printing process adds a protective glass layer to our active meander element. Again, we apply a screen printing mask. Then we press the glass passivation paste through the mask. Finally, we remove the mask. After these processes, we pass our substrates through an oven at a very high temperature. This hardens the pastes. In order to weld our wires onto the sensor, we'll first need to separate the substrate into manageable strips suitable for welding. We do this using a dicing machine. The machine uses a very thin rotating diamond blade. After this process, we're left with strips of sensors, which we can then mount wires onto using our automated welding machine. Now it's time to weld. Wires of different types, lengths, and diameter are welded directly to the reinforced contact pads. At IST's facility, the wire is fed from spools, then it's welded onto each contact pad automatically. Wires of up to 2 meters in length can be welded directly. The wire's insulation is also stripped to the customer's specification. This image shows what a strip of sensors looks like halfway through the welding process. To enhance the welding point and protect it from mechanical damage, a paste is applied to the welding area. This paste is often referred to as a glob top. It increases robustness and allows for better pull strength. The glob top is either left to dry or hardened using a high temperature process. Different pastes are used for different wire types which have varying temperature ratings. Next, the sensor is either diced again or scored and then separated. This depends on the sensor dimensions and the customer requirements. With both methods, we're left with individual sensors. At the end of fabrication, a 100% end-of-line test is carried out, which means each individual sensor is measured at 2 different temperatures. Each measurement is conducted in a carefully controlled bath containing a non-conductive fluid. The uncertainty of our particular measurement environment is around 20 millikelvin. This is achieved by using a 4-wire configuration, by compensating for thermocoupling effects, and by controlling the bath temperatures closely using a carefully monitored and maintained reference sensor. After a 2-point analysis, the technician sorts the sensors, dries them, and prepares them for shipment. Just like with all of our process steps, we record and retain the measurement data for full traceability. Every customer looking for a thin film RTD has a set of requirements for their application. In many cases, they'll find an off-the-shelf sensor which checks every box. Sometimes, though, it's necessary to build a custom sensor that is as unique as the customer's application. Almost every fabrication process we covered has room for customization. Whether we change the size of the sensor, the materials used in production, or the style of the leads, the possibilities are really endless. But we don't customize just for the sake of customizing. In almost all cases, we're somehow adding value to the sensor. Let's take a look at some of the ways we can customize a thin film RTD. Custom wiring is one of the most common modifications we'll make when designing an RTD. On this slide, we see some of the common wire types that we use in production. You'll notice that we've named them with numbers like 3K and 8W. That's because these wires are all rated for different temperatures. Even though we don't use PTFE insulation beyond 200 degrees C, we do have some options for insulation at higher temperatures. Some common forms include ceramic or flexible braided fiberglass. Besides the wire type itself, it's also possible to attach the wires in different configurations to meet the customer's specification. For example, let's say we want to solder an RTD at the bottom of a tube. We'll need to bend the leads in order to fit in the tube. To minimize stress on the welding point and maximize space inside the tube, we can weld the wires on backwards in an inverted configuration, like in the image on the left. What if we're concerned about the resistance of our long lead wires? One way we can compensate for this is to directly weld an additional wire or extend it using laser welding. In the example with the green wire, we have two wires welded to one contact and one welded to the other. This lets us compensate for the resistance of all wires, assuming they all have the same resistance. In the example on the far right, we take this a step further. We take a sensor with two leads, then laser weld 4 lead extensions, 2 on each. Now we can compensate for all wires right up to that laser welded extension point. Since applications and requirements vary greatly, there are many sensor sizes and configurations to choose from. We've already explored some of the standard sensor sizes that are available. Now let's take a quick look at some of the unique ones from IST. First up, we have the mini-sense. At 1.2 by 1.6 millimeters, this is one of our smallest chips. It's optimal for applications where space is limited. Just like with any other RTD, we can directly weld long lead wires. Next, we have the slim sense. At 0.8 by 3 millimeters, it's suitable for applications with tube diameters of around 1 millimeter. Another option is axial lead wires. In this configuration, our sensor fits in a bore with an inner diameter of less than 0.6 millimeters. Notice how the contact pads are on opposite ends of the meander structure. Finally, we have surface mountable devices and flip chips, called SMDs and FCs for short. SMDs are dipped in tin, so the contact wraps all the way around the sensor and it's present on both sides. FCs have contact pads just on one side. These are ideal for soldering on circuit boards and they take up very little space. RTDs can also be housed in a number of ways, making them suitable for a wide array of applications. For example, we can pot our thin film RTD in a ceramic housing. The ceramic is thermally conductive and provides protection for the sensor. The ceramic housing is nearly the same size as some wire-wound RTDs, making it a great drop-in replacement or upgrade. Another option available from IST is the real probe temp. This consists of a mini sense with 4 inverted leads and a metallized backside. It is attached to the bottom of a stainless tube, and it exhibits excellent response time when submerged, regardless of the depth, since the sensor is right at the tip. The backside of the sensor can be coated with a metal using the same sputtering process that we used for platinum in the beginning. This increases the accuracy and decreases the response time of the sensor when soldered onto a metallic surface. This is due to better thermal coupling. Besides metallizing the backside, IST can also build application-specific assemblies. some of which are pictured on the right. We've already discussed some of the common temperature coefficients of resistance, or TCRs, for platinum sensors. Why would we need to deviate from a standard one, like 3850 ppm per Kelvin? Some TCRs are application-specific and have special advantages. It's also sometimes necessary to make a special sensor that will serve as a replacement for a discontinued part. In these cases, it's important to match the original TCR and characteristic curve of the original sensor. Here we can see some commonly used TCRs for platinum and nickel. At IST, we're also able to match common industry standards and customer-specific TCRs. The last customization techniques we'll discuss are pairing and grouping. In some cases, the accuracy of the absolute temperature is not the most important, but rather the relative deviation between two or more sensors. For these cases, IST specially selects RTDs and pairs or groups them together. For example, if the relative deviation between sensors must be between 50 and 100 millikelvin, but the absolute accuracy tolerance may be higher, like Class B for example, IST can sort the sensors at the final measurement and divide them into different groups according to the customer's request. The customer benefits in that all sensors within the group meet a tight relative tolerance, but the price isn't too high because the sensor is still Class B. Pairing can also be used as a technique to avoid calibration after replacing a sensor in an application. During the final measurement process, IST can package each sensor with its closest match. Then, the customer can keep it on hand in case they need to swap out the sensor for a new one. They'll get to avoid modifying any settings on their transmitter. We've covered several common customization techniques, but there are many more. The list keeps growing. IST has thousands of sensors to choose from and releases several hundred new ones each year. Some of these are adaptations of existing products, featuring some custom modification, like a new wire length, for example, while others are completely new designs, developed specifically based on a customer's requirements or based on an emerging need in the field. With a flexible fabrication environment and knowledgeable R&D and production teams with decades of experience, IST is able to provide its customers with sensors at small prototype quantities or scale up to high volume production, making millions of sensors per year. When working with customers, IST serves as a technology resource and partner, helping to provide the best sensor solution for each application, whether it's existing or custom. If you'd like to know more about our existing products or our customization options at IST, feel free to visit our website ist-ag.com and send us a note. Thank you everyone for watching, and again, feel free to contact us anytime to discuss your sensing needs. You can now reach us 24 hours a day, Monday through Friday, on our website's live chat.